thank you for everyone for hanging around. I know it's the last talk of the day, but I want to thank the organizers and KITP. I'm really excited to be here to talk to you about calcium-rich transients and broadly their environments, where they are located in their host galaxies, what they're doing near the white dwarf or near the stars that produce them, which is still an open question, which I hope brings some discussion. So zooming in on a nice nearby calcium-rich transient, this is the host galaxy of 19 EHK. This is an animation we made for some press. This is the supernova explosion, and this is the resulting animation. And I'll get into this progenitor picture a little bit more later, but basically what I want to go over in this talk is what is the phase space observationally, theoretically, of calcium-rich transients. I mean, maybe we don't even understand what they are. It's just another transient class to many of us. But really, the main goal that I care about is what can it tell us about their progenitor systems, because it's one of these classes where the progenitor system is definitely heterogeneous and it's definitely an open question. So hopefully, multi-wavelength observations I can show you are the way forward in peculiar transient classes, especially calcium-rich transients. So to explain the calcium-rich transient class, it really is an observational class initially, and then we kind of gather enough information that maybe it was physically distinct, like other thermonuclear transients. So these are intrinsically faint events. As you can see, this is an older sample of calcium-rich transients where you see there's a pretty fast rise time, fast decline, low intrinsic peak luminosities. And as we've gathered more and more events in later years, we've kind of seen that there is a diversity even in the optical light curves of these events. So overplotted here are more calcium-rich transients. They meet the same criteria, but they have this really interesting feature in less than 5 days before explosion, or 5 days before peak. It's this additional light curve peak. It's even more than an excess. It's an entirely physically distinct emission mechanism on top of a normal radioactive decay powered light curve. So there's one, and then there's two peaks. And so this is super cool. This is not just a one-off thing. We've been seeing this in now 5 events, I think we have. And so these are just a couple I've highlighted here. And the emission mechanism behind this is pretty unknown, but I'll talk to you about some scenarios that I think are plausible. And what's interesting is that calcium-rich transients, we thought at least when we first thought about the class, come from potentially white dwarf systems. So if we think that they come from white dwarf systems, and if we jump to the conclusion, maybe not correct, but that all these double-peaked calcium-rich transients are from a white dwarf, why is there material sitting around it that could potentially cause this really, really significant excess in flux? So that's kind of the motivation behind a lot of what I work on with calcium-rich transients. In terms of their host environments, it's really all over the place. But as you can see, in pink are all the double-peaked events. So just to get an idea of where are the locations of the objects where there might be material around a white dwarf at the time of explosion, to try to convince us that they might actually be white dwarf systems. They're not only found in the outskirts of elliptical galaxies, they're found in the centers of very star-forming galaxies. But in general, when you look at the really local, maybe parsec scale environments of calcium-rich transients, what's interesting is that there's really no star formation. So they definitely sit on the tail end of a star formation distribution. So that points towards a compact progenitor, points towards a degenerate progenitor. So that's cool. And we've only had one case where we've been able to look at the pre-explosion imaging. That was also in this really nice, obviously because the galaxy looks so nice, it was very nearby. We had a lot of HST imaging, and we were also able to look really deep and see that there is no probably unlikely massive star at that location leading to the supernova that was a calcium-rich transient. And so a white dwarf system was favored in this case. So I'm kind of tallying up points for the white dwarf systems and why it's weird that these objects have 2 light curve peaks and weird environments. Spectroscopically is kind of where they get the calcium-rich name. If you look at the nebular spectra, at later times, they're pretty much dominated by calcium-2, forbidden calcium-2 emission. If you take the ratio of the two, calcium-2 to oxygen-2, you can see that the inner regions of the ejector are cooling extremely efficiently through calcium. Doesn't mean that they're necessarily rich in calcium. Rather, they are calcium strong, so strong in emission. I like Ken's terminology there. So I may say calcium strong, I may say calcium rich. I'm so inundated with both terms that but they're interchangeable. It doesn't mean that they have more calcium. But these are really interesting events spectroscopically, and we can kind of confirm calcium richness or strongness by continuing to follow them at later times in nebular phase to see how this dominant calcium line emerges. We're able now, with calcium-rich events, to observe them in days of explosion. So this is 19 HK, which I'll talk about a lot today. And this is the most nearby event, so it was one of the earliest discovered events. And so we took a spectrum when it was first discovered in 2019. And what you may notice on top of this kind of reddened continuum is these narrow lines. So this is photoionized helium-2 and H-alpha. And what this is actually like a direct probe of local circumstellar environment, or CSM, sitting around the progenitor of whatever produced 2019 HK at the time of explosion. So this is the first time that we'd ever had direct evidence for CSM around a calcium-rich transient progenitor. And the fact that these lines are long-lived means that the CSM is pretty dense, ends at some sort of finite radius. It doesn't extend forever. It's some sort of shell because as the shock propagates, it'll continue to photoionize the material. And it's not just the breakout flash that keeps these narrow emission lines illuminated. So that's another interesting point in the calcium-rich landscape. And to show the whole evolution, I kind of made this time series of 2019 EHK and what they look like observationally, spectroscopically. And just wanted to play a movie while I also just talk about some proposed progenitor channels. Over the years, they've been thought to maybe come from stripped envelope massive stars. I'm going to kind of not talk about the progenitor channel because I don't see that the objects I'm talking about fall into that class or potential progenitor system. White dwarf disruption by a neutron star black hole, that's pretty exotic. I don't think we have a lot of evidence for that. But these two white dwarf scenarios, I think, is where hold a lot of promise for producing calcium-rich transients. So low mass white dwarf mergers, disruption, something like that, or some sort of helium shell detonation. And as you can see at late times, we need a model that can produce this very, very strong calcium emission lines. I want to cover the whole electromagnetic phase space with you today because calcium-rich transients actually are interesting outside of the optical. So before I started working on calcium-rich transients and before 2019, we really didn't have a lot of reason to look at calcium-rich transients in the X-rays, kind of similar to 1As. We thought they're from white dwarfs. Why would we waste X-ray time looking at thermonuclear event? So we did look at them at late times to place limits. But what 19HK actually showed us is that they are extremely bright in the X-ray in less than 5 days after explosion. And so this was 19HK in green, so it's a very fast fading X-ray signal. And this was not just one event. Recently in 2021, we found another calcium-rich transient, same double peak light curve, almost identical spectroscopic evolution, and it had bright X-rays at a day after explosion. So these are bright X-ray transients, and our only real hope for getting X-rays of a thermonuclear event like a calcium-rich transient is through I guess X-ray telescopes attached to fast-moving space-based missions like Swift XRT. We have programs to try to do it with Chandra or XMM, but the fast-fading nature of this is really difficult to constrain. So that's a phase space that we really want to explore. But it also continues to indicate that there's material there. There's material sitting around this progenitor star at the time of explosion, which then leads to this luminous X-ray emission because it's just a product of shock interaction with extended CSM. So that's very cool. In terms of, so these are the limits, so it's not the most optimistic for Swift, but for Chandra, we could potentially do better. In terms of the radio phase space, we've also tried to look at them at late times. At early times, as we heard in that really nice talk about radio observations of thermonuclear events, early time radio may not be the place to look if these things are interacting with a lot of CSM. But radio observations are still very constraining because it tells us that at some point, and we think it's about 10 to the 15 centimeters, this shell of CSM in these interacting calcium-rich transients just kind of ends, and then it's just clean. There's nothing out there, so that tells us some really nice things about how the progenitor was losing mass in its final years, decades before explosion. As the shock continues to probe further and further distances, if it's continually clean, that's maybe different than a massive star. So this is really interesting. Perfect. To model the primary peak, I've been really interested, and I have an undergrad working with me, Padma Venkatraman. She definitely works, I work for her, if anything. And she has built this package, a user-friendly Python package to model double peak light curves using all of the available numerical and analytic formalisms that can help us understand the mass and the radius of extended material sitting around any progenitor star exploding. But specifically, I wanted to use it for a calcium-rich transient, and this is the primary light curve peak of a calcium-rich transient 2021 GNO. And these shock cooling models fit very well. So shock cooling is essentially just a one-punch shock interaction. The shock passes right through some extended material. That material expands, cools down, and just radiates thermally and produces this nice light curve peak. It's basically what happens in a type 2b, but now we're seeing it in a variety of events, and maybe we're seeing it in material sitting around a white dwarf, which would be very cool. So yeah, this is very compact material. If this is the emission mechanism, this has to be then combined with this X-ray luminosity, X-ray emission in some events, and then a clean cut in density space at further distances. So combining it all together, I really wanted to make this plot for a long time, and we finally have enough observations to do it. This is basically pre-explosion or progenitor radius, or circumstellar radius and density. So this is the pre-explosion environment of a calcium-strong or calcium-rich transient. This is the first time we've ever been able to understand what the progenitor's system looks like before the explosion. And we can do it through a combination of multi-wavelength efforts. So all these events are the densities and radii found from modeling the double peaked, the first light curve peak with a shock cooling emission. And we see this kind of gathering of high density stuff at very compact radii. And then for the two events that we have X-ray observations for, we can use them to constrain the edge of any circumstellar medium shell and the densities there. And then our further radio observations probe further out distances. And what I'm showing here, which are very consistent, are white dwarf merger models from Joseph Zanotti and Hagai Peretz. And this is just one proposed scenario. We could try to understand this in other ways if you have other suggestions. But this particular model works pretty well with a helium and hydrogen-rich composition. You have one white dwarf that gets tidally disrupted by another, and that kind of leaves a messy environment. And when one explodes in a weak explosion in that accretion, you get kind of a calcium-rich transient, a faint event. So it works. I'm open to more suggestions. I kind of wanted to put this out here because we can really combine many regimes, many orders of magnitude in electromagnetic wavelength space, and kind of complete the rainbow in terms of circumstellar material. So what have we learned? X-ray and radio and flash spectroscopy, early time observations are essential to understand calcium-rich transients. Calcium-rich transients are X-ray bright if we observe them early enough. It indicates a confined shell of material sitting around what we think is a white dwarf progenitor. And these double-peaked events, also indicating some material sitting around the progenitor star at the time of explosion, indicates a very interesting circumstellar environment. And I put in this question kind of just to open it up, just where do white dwarfs fit into this? If these are white dwarfs, we should think about how we can make these systems. So yeah, with that, thank you. I'll take questions.
Thank you, Wynn. Questions?
Thanks for the nice talk. So you said the progenitor was a helium CO white dwarf plus a CO white dwarf, and the helium CO, is that the core composition that you expect, or is that?
It's a sorry.
Is that helium CO is the core composition of the white dwarf?
I believe, yeah, exactly.
With a 0.63 solar mass.
Yes.
I think that's tricky to make.
Yeah.
Yeah.
So the model that was given to me for this paper was helium CO white dwarf accretor, and then it tidally disrupts a CO white dwarf donor, and then the accretor explodes inside that disk. But I want to talk more about that model.
Yeah, that sounds tricky.
Yeah. That's good. I want to know these things. Yeah.
Hey, Wynn. I had, sorry, just two questions. So you said that you don't want to like pay too much attention to the stripped envelope supernova model. Is
Oh no,
that...
not that. I just wanted to talk about it. I think that there are other calcium-rich transients because it's a pretty heterogeneous class that could fit into that. And I think that there have been samples. There's been a really nice 2B sample by ZTF about how that star progenitor channel can produce calcium-rich transients. Calcium-rich transients, I mean, it's only based on how much calcium we see relative to oxygen in the nebula spectra. That could be from a lot of different, it's essentially ejecta structures, but yeah.
And the other question is, do you know anything about the selection effects of these calcium-rich transients? Like, are we missing them within the optical radius of galaxies or not? Because like a lot of them are unusually isolated. So,
yes. Yeah. I think the best systematic study was by Kishlet in the 2020 ZTF census. And there he found about of order 10. But I think that he was pretty complete and felt that there wasn't a lot that he was missing. But I would have to think more on that. I haven't thought about it in terms of populations. I've been working on single events or multiple events, yeah.
I got the mic, sorry. Someone asked two questions. Can I ask two as well? So it's beautiful. Just wondering about the color evolution at the two peaks. Is there anything interesting there? And my second question is about the H alpha. I think there was H beta 2 and the helium 2. They looked very have broad basis at least. I mean, they looked very wide, but they were also very narrowly peaked at the same time. So if you can say anything about the line profile and what that you can learn from that.
Yeah, so for your first question, the colors, very blue during the first peak. Like you can see that it is the color, I don't have a color evolution plot here, but in the papers we have some where during that flare or initial light curve peak, the colors are remaining blue, it's trying to stay blue, and then it transitions into a very red event. Calcium-rich transients are very red. So I think that indicates, there's like there's an increase in that temperature there. In terms of the narrow emission lines, so the base is slightly Lorentzian. And in strongly so the analog is strongly interacting supernovae like type 2N. You get those Lorentzian profiles because you have photons scattering off of electrons, so free electrons, electron scattering. And so I think that that's probably a similar process happening in the CSM around 19 HK. Maybe the densities are not the same as the type 2N, so you're not getting as many scatterings. And then the core of those lines are of order 500 kilometers per second, which I think is a really interesting velocity if we think about white dwarfs and orbitals, like, I don't know, binaries and things like that, because it's definitely less than the escape velocity of a white dwarf. So we kind of had to reconcile that as it's coming maybe from more of the disk and stuff like that. But yeah, that's about what I would say about the line profiles.
So I'm curious about the early peaks in these light curves, which is related to the question Ivo just asked. So it sounds like they're very blue. I was going to ask if they can have any relation to the early bumps we see in normal type 1a, which may also come from merging white dwarfs that also lose some material. So I guess I'm just wondering whether or not these early peaks are all produced by the same mechanism, which here you're attributing to shock cooling of
shock interaction,
some extended envelope, or if they have
it could be a shell. A double detonation.
Yeah, so it sounds like from the event we heard about earlier, that one was very red.
Yeah.
At early times, so maybe that's different, but
so I was looking through figures for this plot, for this talk, and I found these models because I went from doing a paper with Abby where we had all these models for double detonation, thick helium shells, thin helium shells, and then this is the double peaked light curve of 19 HK, and they just are not consistent enough. The colors aren't consistent. The time scales of the peak are not consistent. And I think you have a hard time producing bright X-rays from that as well, maybe. So I think that these are physically distinct things. I really wanted it to be a nice continuation of using the same models for two projects right into each other. But I think it's really cool that, this is a different mechanism. But it's a good point.
Quick question. Are you assuming the X-rays are thermal?
Yeah. they are. So the spectrum, when we fit the spectrum of the X-rays, it is a thermo-Bremsstrahlung spectrum.
And then is it optically thick to the X-rays up until basically the shock breaks out, or?
So you're saying, is it optically thick based on the density profiles that we've assumed?
Yeah, the CSM density is pretty high.
It's high, yeah. I think that, that was our initial thought. Yeah, we really thought about the CSM structure there. Like maybe there's an inner region and an outer region. We invoked a lot of different structures. I think that, yes, you're completely right, that the densities that I invoke from this picture of the phase space would be too optically thick to the X-rays. So then you either have to explain this all in one picture, or this is a completely separate regime where it's maybe like a detached shell of CSM. So that's a complicated picture. You have like a settling of some sort of envelope that produces an initial light curve peak, and then you also have the shock run into slightly more optically thin stuff out to 10 to the 15 centimeters. I think we're just adding pieces to the puzzle here, but yeah, exactly. Really, really good point.
All right, thank you, Wynn, and thank you to all our speakers.